Hello, class. Now we're going into part 3 of chapter 2, where we go into chemical reactions. We talked about physical ways that we can sort of put different molecules, different substances together, whether it be a mixture, a colloid. Those are different ways where there's a physical sort of physical mixing together, but not necessarily chemical. And then we got into some of the covalent bonding and the ionic bonding ways that you can have sort of a chemical difference between, remember, oxygen, hydrogen, put those together, and we can get what we call water, which is different from hydrogen and oxygen. So a chemical reaction has occurred. So chemical reaction is when chemical bond is formed, broken, or rearranged, or electrons are transferred, right? So this may sound a little confusing, but basically it's a chemical change. And when we talk about chemical, we mean a change in the structure of the atom. Remember, the smallest unit of matter is the atom. So a change in the structure of the atom. So change of number of electrons, changes in that structure and that general composition of the atom is no longer the same element. Chemical notation. You see listed here is symbols, abbreviations, which demonstrate what happens in a chemical reaction. We have an equation. We have, for instance, we have 2 hydrogen plus an oxygen equals H2O, water. So two hydrogen atoms plus 1 oxygen atom equals a molecule of water, H2O. All right, so that would be a chemical equation. So on the left side of the reaction, we have the reactants, hydrogen and oxygen, starting ingredients. And then on the right side, we have the product, which would be water, if we're making water, for instance. That is a chemical equation. And here we have a little bit more about that. Reversible reactions proceed in either direction, right? So we have reactions that can go both ways. You can go from the products to the reactants this way, or you can go from the reactants back to the products. That's a reversible reaction. You'll see that you'll see arrows in both directions. And you have irreversible reactions, which are reactions that go one way. So 2 products go to the reactant and they don't go back, and that'll be a single arrow. And it's not showing up here in the slide, but this is carbon dioxide plus water equals carbonic acid. And this is actually a reversible reaction. So the arrows, you would have 2 arrows, one pointing from left to right, one pointing from right to left. Energy. Now you may feel like, well, what does this have to do with chemical reactions? But this is very important because we have to have energy to make reactions happen. Why doesn't all of the oxygen and hydrogen that is in the air around us, this just naturally become water? First of all, that'd be bad, because then we wouldn't be able to breathe if all the oxygen became chemically bound to the hydrogen and became water. But there's a reason why we have oxygen floating in the air. We have hydrogen floating in the air right now, and that it all is not just combining and forming water. It's because it requires energy to do that. Hopefully somebody just had an aha moment. You just were like, oh yeah, why doesn't that happen? That's exactly why. So we need to talk about the role that energy plays in this, in chemical reactions. All right, so energy is the capacity to do work or put matter into motion or fuel chemical reactions. Okay, so kind of a long definition. Energy is doing something, is the capacity to do something, put something into motion, provide the energy to fuel a reaction. That's what we're going to define as energy, which is a little arbitrary, kind of hard to understand sometimes. But here's a good example. Potential energy is stored and can be released later to do work. So if you see the ball here at the top of the hill, because if I let it go, it's going to roll down this hill. So it has the ability to move, the potential to roll fast to gain speed down this hill. Kinetic energy, potential energy that has been released or set into motion. So once this ball is let go and it rolls down this hill, all the potential energy is converted into kinetic energy. And the ball picks up speed and it goes really fast, and then it slows down and stops. And then it has, at the bottom, it has no potential or kinetic energy because it has no reason to move. All atoms have kinetic energy. Right? So that's general energy. Now, there are 3 forms of energy in the human body that we want to talk about: chemical, electrical, and mechanical. These are all very important, and each can be potential or kinetic. Right? Chemical energy, in between the bonds between the atoms. When we talked about covalent bonds and ionic bonds, those bonds are being held together. There's energy. You have electrical energy generated by the movement of charged particles or ions. So, for instance, electricity. Think of electricity, movement of electrons, electrical energy. And then you also have mechanical energy. Think of muscles moving. That's energy directly transferred from one object to another. So I think my body sends a signal to my bicep, which causes my arm to grab my coffee, pick it up, bring it to my mouth. Mechanical energy. Right, so chemical, in between the bonds, electrical, movement of charged particles such as electrons or ions, and mechanical energy directly transferred from one object to another. All right, usually involves movement. Here's where it can get a little confusing, if it hasn't already got confusing, is we also have different types of reactions. We have ender and exergonic reactions, right? Ender, even though it's N-E-N, think of N-I-N, think of ender, requires an input of energy from another source. So this is a reaction that you need energy to be put into the reaction for that reaction to happen, right? Hydrogen plus oxygen equals H2O is an endergonic reaction. You need energy to be put into that reaction for that to happen. Otherwise, the hydrogen and oxygen will just float around in the air and never make water. Right. And so in this situation, the product contains more energy than the reactants, because the product, so you have reactant plus energy equals the product. Exergonic is the reverse, basically. You have usually it's something being split apart and it releases energy. So you have the reactant may be one or two things maybe, and to get to the product, it releases energy. That's an exergonic reaction. So think of energy as escaping, exiting the reaction. All right, so you have endergonic, requires input of energy. Exergonic, energy is released. All right, so we also have to further challenge this topic, and it's all going to actually come together, even though we're talking about all these terms: chemical reaction, electrical, mechanical, products, reactants, endergonic, exergonic. Even though we're talking about all these terms, it all does come together in the end. So here we have three fundamental processes maintain homeostasis. These three types of reactions are Catabolic, breaking things down. Exchange reactions, we go from two things to sort of the same two things, and then anabolic reactions, building things up. So usually in catabolic reactions, we see the reactant is like a bigger molecule, and it gets broken down into two molecules, two different things. In anabolic reactions, we usually see two reactants that get combined to make up a single product. Anabolic tends to be endergonic, catabolic tends to be exergonic. All right, so let's talk about those in a little more detail. All right, so catabolic reactions, decomposition reactions, a large substance is broken down into a smaller substance. Happens all the time in your body, right? These catabolic, so endergonic, exergonic. Endergonic requires energy, exergonic releases energy. Catabolic, breaking things down, anabolic, building things up. All of these happen in your body. Catabolic is generally AB, so a big molecule broken down into A plus B. That's the general chemical notation. Usually exergonic, chemical bonds are broken. Oxidation reduction. These are kind of an exchange reaction, right? We're going to talk about, this is what happens in a battery. But in the oxidation reduction reactions, you have a reactant that's oxidized, loses electrons, and a reactant that's reduced gains electrons. Now you may say, well, why do we call it the one that gains the electrons reduced? Remember, electrons have a negative charge. Therefore, if I add electrons to something, I'm reducing its overall charge. So that's how you remember it. Oxidized loses electrons. The reactant, the one that's oxidized, is losing electrons, and the one that's reduced is gaining electrons. Redox reactions are usually exergonic reactions. We also put, they're usually exergonic. It means they release energy, release large amounts of energy. They're also considered exchange reactions in the catabolic, exchange, anabolic category. And then we have anabolic reactions, synthesis reactions, where we take A and B, put them together and make AB, make a larger molecule. Those generally are endergonic, like I said, require energy. Okay. And they're generally fueled by chemical energy. So catabolic breaks something down, anabolic builds something up. If you've ever heard of anabolic steroids, which a lot of weightlifters use, have used in the past, and I think they're illegal in a lot of competitions, but it's used to bulk you up, build you up. That's the whole concept. You're building protein in the body, building muscles in the body. Right, so now let's get in. So we talked about energy, we talked about different types of reactions. We also we're getting deeper into the body now, and we're getting into reaction rates and enzymes. Right, so for a reaction to occur, atoms must collide with enough energy to overcome repulsion of their electrons. So for a reaction to happen, they must kind of, the reactants must collide, must come together with enough energy to be able to react. Remember, they all have electrons on the outside, and their valence electrons, those negative electrons would naturally repel each other. They wouldn't attract each other. So for them to come together and react, we have to have enough energy so that we can overcome that natural tendency to repel each other. That is where we come to the concept of activation energy. Activation energy is required for all chemical reactions, right? So if you remember that ball on top of the hill, to get that ball on the top of the hill to where we have all of that potential energy, to get it to the top of the hill, somebody have to pick it, push it up there, right? To get to the top of that hill, that energy to get to the top is called activation energy in the sense of chemical reactions. And then once we have that energy, now we can get over, now the ball can start to roll down the hill by itself. And so that all that potential energy that's stored up now can convert into kinetic energy. In the sense of chemical, we have the reaction. So the activation energy is the energy just to get two reactants, one reactant, reactants to react. So here's another good chart to look at it. Right. So you start off, think of hydrogen and oxygen. They would normally just float around in the air by themselves. They wouldn't do anything. But if you get the right amount of energy, heat could do it. If you get both of them hot enough, now they start floating around faster and banging into each other. We could overcome this activation energy, get them to this point, and then they would react and form water. Right? So that's the idea. That's what would happen over time. So activation energy must be supplied so that reactants reach this transition state and sort of get to the top of the hill so that they can react and form the products that you want them to form. So how does this happen in your body? That's what we want to get to. This is human anatomy and physiology. We are studying the body. We're not just studying chemistry, even though chemistry is very important for understanding what's going on inside of your body. So the following factors increase reaction rate by reducing activation energy or increasing the likelihood of strong collisions. Okay, so we have concentration. So the more reactants that we have, the more likely they're going to bang into each other. So that would be the more likely they would react. Increasing the temperature. Heat is energy. All right, increase that energy, increase that temperature. The hotter something is, the more it's going to move around. Increase, that's why we heat up food when we're cooking it. The reactant properties, we can work with the properties of the reactants and change those slightly. We'll talk about how that can happen. And the presence or absence of a catalyst. Now, this is where we get into enzymes, which are in your body. Right, so when concentration increases, like I just mentioned, more reactant particles are present. Increases more, if you have more reactants there, more likely they'll collide, more likely they'll react. Makes sense. Raising the temperature increases the kinetic energy. More movement, more chances they'll bang into each other, more chances they'll react. Those both make sense, hopefully. Particle size and phase influence reaction rates. Smaller particles move faster, more energy. Reactant particles in gas phase have higher kinetic energy than either solid or liquid phase. So if something is in a gas versus in a solid, it'll be more likely to react. So that's changing the reactant properties. And then we have what we call catalysts. A catalyst increases reaction rate by lowering activation energy, but it is not consumed in the reaction. And in our bodies, we have a natural catalyst, which we call the enzyme. And these are all throughout our body. And basically all that enzymes do is speed up reactions by lowering the activation energy. So if an enzyme is available, it can help lower that activation energy, the energy that is necessary to get that reaction started, and therefore allow that reaction to happen more likely in your body. Right? The way that it does this is highly specific for individual substrates, which bind enzymes' active site. We're going to talk about that. They do not alter the reactants or the products, and they are not permanently altered. Their whole goal is this first point: speed up the reactions by lowering the activation energy. And most of the enzymes in your body are proteins. Right? So taking you back to our diagram, normally you'd have to push the ball up to this kind of hill. So this is the activation energy you'd have to overcome to make a reaction happen. But with an enzyme, you don't have to push it up as high. That's the whole concept of an enzyme, is that it requires less energy to be able to have the reaction. And this is a diagram of an enzyme. Basically, if you take two substrates, two reactants, they bind to the enzyme. This is the enzyme here. It brings them very close together. They both fit into the enzyme, and then they therefore come very close together and thus, collide with each other and react. So the enzyme makes it more likely for these two to react together. Reduces energy of activation. So you reduce the activation energy because you bring them so close together. Allows transition state to proceed to final products, and you get the product that you were looking for. So if these two were just simply floating around in the air, as you see here, they would have a less likely chance to react. You'd have to raise the temperature, increase the concentration. But since you have this enzyme here, this purple glob here, it allows them both to fit in there nice and conveniently. They react more, they're more likely to react and produce the product. That's what an enzyme does. We always want to look at issues whenever we are discussing different parts of the body. You don't have to memorize these, but these are some things you may find depending on which line of work you go into after you leave. After you leave this educational environment. Tay-Sachs disease, a deficiency in hexosaminidase. Gangliosides accumulate around the neurons of the brain. Unfortunately, they see death by age 3. These are enzyme deficiencies. So therefore, because of the deficiencies in these enzymes, the body can't do the reactions necessary to sustain life. SCID, severe combined immunodeficiency syndrome, maybe due to the adenosine deaminase deficiency, which results in reduction of the absence of the immune system due to the lack of this enzyme. All right, so enzymes can play a huge role in our body's function. Remember, our body has chemical reactions that need to happen and has enzymes all over the body. So if you have an issue with the enzymes and these reactions that are supposed to happen don't happen because your body can't overcome the activation energy naturally, then it can become very problematic. Here we have some inorganic compounds, section 2.4. We're going to talk about waters, acids, bases, and salt bonds. We're going to talk about inorganic and organic. But first, we're going to talk about inorganic. Biochemistry is the chemistry of life. Inorganic, and when I say inorganic and organic, you may think when you go to the grocery store, for instance, you say, oh, this is organic. Organic in the grocery store and organic in chemistry are two different things. All right, just to break that confusion. In the grocery store, when something says it's organic, basically what they mean is they didn't use any pesticides, any hormones. The cow ate grass, natural grass. It wasn't fed any chemical containing food while it was, growing into a full grown cow, or the vegetables weren't sprayed with pesticides. The ones that got eaten by bugs were just eaten by bugs. So that's what it means in Whole Foods or grocery store. Organic in chemistry has a totally different meaning. And so sometimes people get that confused. They think organic, they think, oh, that means all natural. No, that's not what it means in chemistry. In chemistry, organic means a compound that is bound, that contains carbon bound to hydrogen. And you may say, this is, you might say this is something that is, the two are not related, and they really aren't, because saying something is chemically organic has nothing to do with the organic that you hear about really has nothing to do with the organic you hear about in the grocery store. I don't know why we use two different terms. I feel like we should use something different in the grocery store, but that's another class. Right, so inorganic do not contain carbon bound to hydrogen. So you won't see carbons with hydrogen. So water is oxygen bound to hydrogen, H2O. Water is considered inorganic. All right, bases and salts are also considered inorganic. Organic compounds, as you see here, contain carbon bound to hydrogen, right? So like glucose, for instance, is a six carbon chain bound to hydrogens. That is considered organic. All right, so that's a little confusing, what's organic and inorganic, but that's what it means. Simple as that. All right, so water makes up 60 to 80% of the human body. Very important to know that. You see, I have it highlighted in red. Water has so many different functions in the body. High heat capacity. Your body has to maintain a certain temperature. So because you have a whole bunch of water in your body can maintain a certain temperature easily because water can absorb a lot of heat without changing temperature drastically. Your body sweats, and so it can cool itself by that water evaporating and removing heat from the body. Water provides a cushion to help for the structure of the body. Water acts as a lubricant between two adjacent surfaces. In a lot of your joints, there's water in the joints to help lubricate. Water serves as the body's primary solvent. Some people call it the universal solvent because so many things dissolve in water. There are things that do not dissolve in water. We'll talk about those, but remember, water has a partially negative and a partially positive. Remember, we talked about it as a polar covalent bond. And so because it has that partially negative side and partially positive side, it can, it's good for that helps it have the ability to be able to dissolve like lots of different solutes. Things that dissolve in water are called hydrophilic. So hydrophilic solutes, which are usually substances that have a partially charged end, also similar to water, like dissolves like. And so things that are slightly ionic, slightly polar covalent will dissolve well in water, like NaCl. Salt is ionic. So salt dissolves in water. Everybody knows salt water, for instance. Things that are not polar or not ionic, like fats, do not dissolve well in water. Those are called hydrophobic. So hydrophilic likes water. Hydrophobic, phobia, scared of water, doesn't dissolve in water. Right? So they do not have full or partially charged ends, and they're not polar, not ionic, and so they're considered non-polar or uncharged, and they don't dissolve well in water. Next, we have acids and bases. All right, so water considered inorganic. It does not have carbon bound to hydrogen. There's no carbon in water, so it's considered inorganic, even though it's 60 to 80% of the body. Acids and bases also considered, for the most part, inorganic. Acids and bases, as you see here, is really the study of hydrogen ions. So water molecules in solution dissociate break into positively charged hydrogen, negatively charged OH, right? That's the H2O, right? So that's how the water breaks apart. H2O hydrogen ion plus hydroxide ion, so the positive and the negative. An acid, and we're going to talk about acids and bases throughout this class, and so you'll see like this being brought up again and again. An acid is a hydrogen ion or proton donor. Remember this hydrogen ion here, H plus is basically just a proton, right? That's basically what that is. A hydrogen ion is a proton with no electron, because the electron has been removed and pulled off by the OH negative. Okay, so an acid is a hydrogen ion or proton donor. So the number of hydrogen ions increases in water when acid is added. A base, or you'll see the term alkali, is a hydrogen ion acceptor. The OH negative is a hydrogen ion acceptor. Number of hydrogen ions decreases in water when a base is added. So if I add in something basic, something with a negative charge to the water, the H pluses, the hydrogen ions, will be attracted to that and want to combine with it and therefore be reduced. If I add in something, with that is a hydrogen ion or proton donor, it's going to donate hydrogen ions in the water, and therefore there'll be even more hydrogen ions in the water when an acid is added. Okay. So here we have, if you add an acid, such as hydrochloric acid, it'll dissociate in water. You'll get the chlorine. You'll get more hydrogens in the water. If I add in a base, sodium sodium carbonate, here you'll see that it'll dissociate. The HCO2 will dissociate, and therefore it will, when the HCO3 dissociates, it will bind those free hydrogens, and so there will be less free hydrogens. That's how you know it's a base. And so why is that important? Right, here we go. pH scale ranges from 0 to 14. You probably have heard of this pH. Simple way of representing hydrogen ion concentration of a solution. pH is negative logarithm of hydrogen ion concentration. So pH is negative log of hydrogen. 7 is considered neutral. So if something has a pH of 7, it's considered like neutral, water, pH of 7. You have an equal amount of hydrogen plus and OH negative. That will be considered 7. If I add in an acid, then I have more H plus concentration. And so then my pH gets lower. If I add in a base, then I have less H plus concentration. So then my pH gets higher, right? Because it's the negative log of the concentration of the hydrogen ion. So the more hydrogen ion I have, because it's the negative log of that, therefore the more acidic I get. But the less hydrogen ion that I have, the more basic it gets. So hopefully that makes sense. So I add an acid in, I get more higher H plus concentration, more hydrogen ion concentration, I get more acidic. I add a base in, that the base binds to those free hydrogens. Therefore, I have a less hydrogen ion concentration. Because it's the negative log, my number goes up and I become more basic. And then it would be the reverse if you were looking at the OH negative concentration versus the hydrogen ion concentration. And we have what we call a buffer. And this is where we get really into the anatomy and physiology. We get into buffer systems. We're going to talk about this in the blood especially, but also in other parts of the body. Buffer is a chemical system that resists changes in pH, prevents large swings in pH when the acid or base is added to solution. Your body is at a specific pH. You see the blood pH here, 7.35, 7.45. Your body stays in that range. Your body does not want to get to like a 5 pH, which is acidic, or a 9 pH, which is basic. It wants to stay right around there, pretty close to water. So we have this, an example, there's multiple buffers in the body, but one buffer we have is the carbonic acid buffer. Carbonic acid, which can go, this should be a double arrow. It can go to a hydrogen ion or bicarbonate ion. So which this has a positive charge, this has a negative charge. Because we know that, because I just told you that the blood has this narrow range of 7.35 to 7.45, which it needs to maintain homeostasis. We need this because certain reactions happen in the body when your body is at this pH. And if you raise the pH or lower the pH too much, certain reactions in your body won't happen. Therefore, your body has to stay at this specific pH, otherwise you're going to get into some serious trouble. So we have these carbonic acid bicarbonate buffer systems. And so if too much acid gets into our bodies, it makes more, it releases more, we release more of this bicarbonate ion. It binds up those hydrogen ions and neutralizes it that way. If too much base is introduced into our body system, the carbonic acid goes into reaction, releases more hydrogen ion. And so we'll talk about that. This is what helps our body be able to maintain the pH. We also have salts and electrolytes. Salt is any metal cation and non-metal ion held together by ionic bonds. Remember NaCl that makes salt. That's what we call salt, table salt. But salt is any metal cation, non-metal anion held together by ionic bond. Remember, the chlorine steals an electron from the sodium. And so the chlorine has a negative charge, the sodium has a positive charge now, and the two bind together because they're opposite charges. These can dissolve in water and form cations and anions called electrolytes, capable of conducting an electrical circuit.